This is the instructional video for the simulation and optimization vignette that is just now being released. So to start out, of course, this demo is going to be in the same kind of folder structure and the same organizational structure as all the other demos that we put out. It's going to be under simulation and optimization, and our top level assembly is going to be called enginehoist.asm. Now we also have the setup folder with our movies, files to copy, backup, all that. It's probably going to be a little bit different by the time you get this one because I'm still cleaning all this up. However, we also have the script here, which is going to be the as presented script to use for the marketing messages and things of that nature that can be seen on the as presented video. So you'll notice as we go into Solid Edge that we have our theme set up for our presentation theme. If your Solid Edge does not look like this, you need to run the demo setup pack and go ahead and a lot of this is already automated for you for these customizations that you're going to see. So first thing you're going to do whenever you come in is we have an engine hoist. First step is going and turning off perspective because you don't really want to model in perspective unless you've practiced it a lot. The second thing we want to do is change the display configuration. So since we're going to do a beam analysis is the first step, go into frame components for the display configuration. It's going to change everything. You'll notice that this is now a beam representation as well as these back legs right here. Next step is go ahead and go into frame. This guy will actually be pulled in whenever you do, and once in frame you can either undock the simulation from the ribbon or from the edge bar over here. There's a simple bug right now that's in the process of being fixed that if you right click on simulation over here, it's going to pop out this this second box that's going to kind of get in your way, and we don't really want that. So if you just go up and click on new study up in the ribbon, that's a workaround until the fix comes out. It should be available in the next ST8 MP, which would be I think MP3. So we're going to have a linear static study with a mesh type of beam. Go ahead and accept that. And this is another bug that we have whenever you fin select these. Even though you fin select all of the objects, you still have to go back and manually select those three beams. Like I said, that's currently being filed and should be a fix relatively soon as well. Now, one thing to notice: the only things that you can analyze for beam analysis is framework. So none of this stuff, these casters, these are sheet metal and part files, so those casters aren't going to be selectable, as well as this bracketry up here. That's a sheet metal bracket, and that's not selectable either. So only framework is going to be selectable, like you see here, and just right click to accept that, and you're going to see that all of these members are going to connect for your beam analysis on the simulation. Next thing we're going to add as a side note, once you create the study, you can work out of this edge bar as much as you want to. It's just on that initial setting up your simulation study. Next thing we need to add is a load. So for our load, rather than put it on the entire curve, you want to go up and change it over to node. You're going to click on the node, and then you want to reverse the direction because it's going to be on this outside tip in the downward direction. We're going to change it to 20,000 newtons. Now, for those of you who use more American standard, that is going to be equivalent of 2.5 ton force load capability. So 20,000 newtons for the force. Now we're going to set up our constraints. So for our first constraints, we're going to create fixed constraints. Now once again, rather than doing it through the entire curve, through the entire leg, we're going to fix point constraints to where all of these casters are located. And another thing is, after I do the first selection on the drop downs, I'll usually just go up and mouse over the drop down menu and then just scroll my mouse wheel up, and it'll automatically select it and not force you to go through those other mouse clicks. So go ahead and zoom in here, and we're going to place these fixed constraints over all the casters. Once we've got that, we've just got one more set of constraints to put on, and this is going to be a pinned constraint. Once again, we're going to use node, and it's just going to be at the bottom edge of all three of these frame members. Alright, so that's going to represent how this whole thing is going to react, that these are going to be a pin constraint. Once we have that in place, we have our simulation study set up. You don't have to do any connectors within the beam analysis environment because it automatically connects them all for you. So you can just right click and do a mesh. So once you get the mesh dialog open, we're just going to show this is a quick and dirty solve. So you know, don't worry. Well, there aren't any options available for it, but just go ahead and run through your solve. It's going to process the results, and we're just making sure that our stress, our maximum stress on this top beam member, is not going to exceed our yield stress of 380 megapascals. All right. And secondly, the second thing we want to do is come around to the backside and take a look at these two members. And you can see that these two being in green, that they're overbuilt for the situation that we're in right now. So we need to actually mention inside of this simulation demo that not only is solid edge simulation great for making sure things are strong enough, but also making sure that things aren't too overbuilt and we're wasting money on stock material. So those are overbuilt. We're going to close the simulation results and go back out to the frame, and then we're just going to change out these frame members. Now for the frame members, we're going to edit our definition, and then we're going to select the path step. And for these frame members, these are actually going to be placed into the auto demo setup pack. So it's going to replace your DIN standard round tubing because these have different materials associated to them. So just make sure you run that auto demo setup pack. But we're going to change it from the 51 times 3.6 to the 30 times 2.6. So you have to be careful though whenever you're doing that. Because if you don't use the frames that are delivered, you're not going to get that yield stress show in the results, which I'll show you in just a second. So right click to accept it, click yes to apply it to the selected cross member, and then finish, and then do the same thing on the other one. So same steps, go ahead and select path step, drop down round tubing 30 times 2.6.par, click yes once again, and then accept it. At this point, you want to show that our study is out of date and that we need to go and do another solve on this. So we need to resolve. It's going to go back through 4 or 5 seconds, and then zoom in and show that this is more appropriate and that we can get away with using these beams here. Now the reason that you want to use the delivered framework or this round tubing is because if you don't, it's going to be a different material than the rest of the frame, and it's not going to show you a yield stress, and you want to make sure that that yield stress is shown at the bottom at 380 megapascals. So you just want to make sure that you utilize those. Another thing that you want to show is being able to probe these objects, right? Being able to probe and show the different stresses at any particular location on these beams, as well as go over to color bar and do your minimum marker, maximum marker. I just do maximum marker because that's what we want to kind of show as far as areas of concern for the stress are located. Okay, so that's going to do it for the beam itself. So we can close out of the simulation results and close out a frame. And then for the next thing we're going to take a look at is going to be our leveler. So change your display configuration at the top level assembly to leveler, and we're going to be looking at an engine hoist leveler. Now for those of you who don't know what this is basically something that you hang that you're going to hang any kind of weight from. As you can see here, you're going to hang the weight from it, and you slide this leveler back and forth to be able to balance out your engine. So it's usually comes along with these engine hoists. So first thing you want to do is we want to see the internals. We want to see how this whole thing works. So go to your View tab, and then we're going to look at a clipping plane. So the first face you're going to click is on this outside bracket, and you're going to slide this all the way back. You also want to make sure that you have dynamic clipping turned on. So your first click was here, second click on the outside, and then dynamically clip back away. Now as you get close to the middle, go ahead and just scroll in so that you can zoom up so that you can see that that this is basically a bolt that's running through this adjustment bracket, and it's on rollers. So these rollers are going to be taking the brunt, or pretty much all of the force, as they roll up and down this beam. So after you've done that, just go ahead and right click. That'll close it out, and doesn't set the plane, so you have to go and then turn it on and off. And we're actually going to get into our simulation study. So double click on simulation geometry, and we're going to click on the mid surface option. So we're going to represent both of these as mid surfaces. So you can either do offset from side 2 or offset from side 1. It doesn't matter because we're going halfway in between. So just click whichever one you want, right click to accept, right click to accept, and you'll notice that it has that surface located there. And one more quick tip whenever you're running through these: if you ever get it zoomed in and you have some rounds that are a little bit choppy, on your auto demo setup pack, if you hit the F12 after you've run and are in the theme for presentation theme, it'll automatically sharpen that up for you. So that's something I use oftentimes whenever we're looking at any kind of round edges or anything like that. So we're still inside this command. Go ahead and do the exact same thing for the other side. After you do it the first time, you no longer have to select which side you want to offset from, so you can simply right click and right click to accept. Now at this point, we want to get our geometry showing that we're going to be using for the study. A good way to do that, and also hide things that we don't need, I'm just going to select this weld on the beam, and it's going to automatically scroll to the assembly scroll the assembly pathfinder to the feature, and you can turn off that fillet weld. And then you also have these welded sling sides, and those are going to be the sheet metal parts that we can turn off as well, so that we can show those mid surfaces for selecting our geometry. At this point, you can either click over in simulation up here and do a new study. I like to undock the edge bar and just run everything from this point. So right click on simulation, click new study, and this is also where you show that we not only want to do TET meshes, but we also want to do surface meshes as well, because we have these surfaces in here. So we want to be able to pick up mixed and general bodies. Click OK. You're going to pick up both of those surfaces you just created, the main beam, and then the rollers where all the force is going to be collected. So, and pick up those rollers as well. We don't want to get the bolt, and we don't want to get this adjustment bracket either. So we have proper representation, and the bolt is going to be used for reference to see how far this is moved. So go ahead and right click to accept that geometry, and then we're going to set our loads. So right click on loads, go to force. We're going to do an edge or corner selection option, and just pick up these two holes. Switch the direction, and then put in 20,000 for our force. Next thing we want to do is set up our constraints. So we're going to set up a fixed constraint. On this one, we're going to go to the drop down and click on feature, and you're just going to either zoom in or just mouse over where the top of these rollers are. And on one of these face sets, you're going to see that there's been a plane created so that we can represent contact between that beam and the top of those rollers. So I'm going to select those face sets, and here I'll turn that off real quick so that you can see, rather than just being a point tangent to those two, it's an actual surface that we can utilize for simulation purposes. So we're going to set our fixed constraint, and then on this one, the last thing we need to do is set up our connections. Now this is a really cool capability that you want to point out, is that we have all these different manual bolted edge connections that we can do, but we also have an auto connection option. On this, we're going to set the value to 5 for your search distance, and then you can simply fence select the entire thing, and it's only going to pick up the geometry that's part of this simulation study. Once you select all of that, right click, and it's automatically going to interrogate the model, and you should get 8 connectors that are going to form. And this is going to be all of the different contacts between the edges, the rollers, the beam that are located inside of the study. Go ahead and create your connectors, and then you can show how they're going to be placed over here in our connector collector. So now that we have everything set up, we've got our loads, we've got our constraints, we've got our connectors. Now we can go to mesh. So for the mesh, we want to look at some of the options we have for your mesh sizing, your solid meshes, your surface meshes, all of the different options that are available to you. We're going to keep the defaults because it's optimizing speed and accuracy. And then we're just going to do a mesh and solve. Now the mesh and solve doesn't take a whole lot of time, but you talk about improving your performance using tools like the mid-surface and things of that nature. Now for whenever you get into the results, I really like how this ends up showing, because this is how it would fail if this beam were to fail. But we also have our bolt here for references as well. Just say, this deformation is an exaggeration of what actually would happen. If you want to see the actual deformation, all you have to do is click on actual, and you can animate this as well. So click on animate, scroll down, you can look at how far it's moving. We're not really interested in stress, but we're mostly interested in displacement. So click over to displacement. You can actually do that before you do the animation, and show how far this guy is moving. So we're at 7.32 millimeters. We're approaching 8 millimeters. That's going to be too much for this beam, because if it moves too much, it's not going to be able to travel along that threading. So we need to make some changes. So close out of close out of your simulation results, and this is a good time. And it looks good, but it's also necessary for the solve. Hit your control spacebar, and then on this front face that you're looking at, select that front face. That's going to bring up this dimension as well as this thickness. So we need to make some minor changes to these, and then we're going to run through and optimize. So for the 1000, you just talk about how easy it is for Solid Edge and Synchronous to be able to update your model. So type in 600, hit enter, and it's going to automatically go through, and it's going to reassociate all of those simulation features to the relationships. And then you're going to click on the 2 millimeter thickness and change that to 3. It's automatically going to update the thickness on the entire part. At this point, you say, we could go through and guess and resolve and try all of that stuff manually. However, Solid Edge provides you a great tool to be able to do that, called optimization. So we're going to create a new optimization, and we're going to define our objective. Now our objective is going to be to have a total translation, so that was click down, displacement, total translation, and we want to reach a target value, because if you do a minimize, it's going to make it as short and as fat as possible so that it doesn't deform at all. And maximize doesn't make any sense here. So we want a target deformation of 1 millimeter. So just type in 1 and hit enter. Go to next, and now we need a limit. So our limit is actually going to be our stress, and it's going to be our von Mises stress. And since our factor of safety is slightly goofy right now in the way that it's acting, we're going to just use von Mises stress, but we're going to set that value as less than or equal to a factor of safety of 2, which would be half of 380 megapascals, which is 190 megapascals. This is also, you have to set this part as greater than or equal to 0, and this part is less than or equal to 180 megapascals. Once you get that, click next. And then for our design variables, we're going to add peer variables, and we're going to add the exact same variables that we just edited inside of our sling beam part. So that's going to be the ones that you just set to 3 and 600. You can simply click peer variables, click this guy, and then you just hold down your mouse and can go over them. You don't have to hold control or anything like that, and then just hit add. You'll notice that I have a range already built in, so you don't have the repetition of going in and adding more ranges for each individual variable. This is going to be set between 2 and 6 millimeters, and this is going to be between 400 and 1000 millimeters. this point, click Next. Max number of iterations set to 20. Then the converge parameters are going to be set to default. So we're using default for all of the converge parameters. At this point, you're just going to click Optimize. Now, while you're optimizing, you're going to go through 6 iterations, and that's going to take about a minute to run through all of those. Now, if you look at the script that was delivered alongside, there's a lot of great information there as far as what's taking place as it iterates, as well as making sure you point out that this is FEMAP and NASTran that is powering the solving, and the amount of time saved without any kind of designer input, and being able to find the most optimized condition for your solve. So it's just going to go ahead and run through this guy actually pretty quickly. And then once it converges, you just simply click on View Summary. It's going to load it up inside of Microsoft Excel, and then you want your final numbers are going to be around 5 millimeters for your thickness and right at 700 millimeters for your length. So since they don't make stock sizes in 5.075 and 692.622 millimeters in length, we're going to round to 5 and 7. Go ahead and exit out of that. Don't save. And then you want to go in and look at your optimization results. This is there's not a very easy way to do this to get to it, so you're just going to have to click down through it. You'll notice that I only have results for iteration 5. There's an option inside of the optimizations whenever you run through it, where you can have it just show for the final optimization result, and you're going to double click on displacement and then go into total translation. Now, in this version, which actually has been fixed, whenever you click on displacement, it's going to show you a displacement output, but it's going to also remain on stress for whatever particular reason. If you click back on displacement, it shows you the previous model. So it's a little bit messed up where it's currently being fixed. If you go back into it, it does it in the proper way. At this point, we're going to do the exact same thing. We're going to click Actual and then go into Animate. Zoom in nice and tight. Make sure that you can see that we don't have deformation over 1 millimeter. Everything got solved properly. Also show that on this animation you can save them out as videos if you want to. Of course, we're not going to save any of that out. You can use it for marketing materials, whatever the case may be, and that you can also create a report. Now, if you haven't done the first look and you're showing this standalone, go ahead and create a report at this time. There's information on how to do it and how to populate it within the script. If you've already done the first look, it's a little bit repetitive showing the same steps to create the report, and the worst part is it'll still have all of your first look information in here that you'll have to alter. So we've also delivered under the working folder, an engine hoist static study that is going to be available to you guys, so you can simply go through and show what the report output would be, control click for results and scroll through and show that all of this is automatically generated, much like you saw in the first look. So some really nice stuff there. And then as I'm closing it out, as I'm talking about what it is that they just seen, I go ahead and start cleaning things up a little bit, just so that I can go back to show all, collapse everything down, just so that we have a nice view as the whole thing closes of the cherry picker assembly. So that's the new simulation and optimization demo.